So I think so. In the way, if you have seen the lectures by the professor, you can see that there are a lot of mathematics involved in support vector machines. But I will try to explain in a way such that there are no at least minimum mathematics are required, right? So I'll try to explain it in a conceptual and from a uh, machine learning standpoint, right? And how to uh, actually implement it from an implementation point of view, right? So, okay. So let's say, we have seen an example of logistic regression, like how you can classify a set of uh, mice into obese or not, right? Now, let's say you have the same example. You have some set of mice, and these are the weights of those mice, and you are classifying them as obese or not. So the red ones are the not obese, green ones are obese. So these are your data. Okay, this is the data. Let's consider the first row. Okay, I'll then sequentially go into the next uh, next rows. Okay, so in the first row, this is your data that you are given, and you have to classify them as mice or not. So sorry, classify them as obese or not. So you can like visually see that if you like draw a line over here or here or here, you can just separate them into uh, obese or not obese. So anything that lies on the left of that line is not obese, right of that line is obese. Okay? But the question is how to decide which line to take. Now come to the second picture. So here, let's say if you have chosen this line, okay. So is it a good way to classify obese or not obese? No, right? Because let's say if you get a new example, which is given and shown in black over here. So this example would be classified as obese according to the line you have drawn, because on the right of the line, you are just telling everything is obese. So this example lies on the right of that line. But you see, this example is closer to the set of non-obese mice, right? And it's farther away from the obese mice. So what will happen is that this is not a good idea. This is not a good line to classify them as obese or not. Right? On the other hand, let's come to the third picture now. What if you choose this line as your classification line? So everything on the left is not obese, like obese. So this is uh, better choice actually, because this is uh, not as close to this to the red set of points and not as close to the green set of points as well. It's somewhere in between. Now, what will happen? Okay, so there is one terminology before moving on. So whatever the line is, the distance of the closest red point is from this line is this distance, okay, and from the closest green point from this line is this distance. So these are called margins, okay. This is just a terminology, right? So for example, if you shift this line towards your left, the red margin decreases, whereas the green margin increases, right? So this is one way to classify this. But again, the question remains like, which is the best orange line that could classify these examples? So now moving on to this thing. Okay. So if you uh, put this orange line exactly in between the nearest green example and the nearest red example, that is basically called the maximal margin classifier, because then only you will have this maximal margin. So if you shift this orange line towards the left, this red margin will decrease. So that is not the maximal margin. Okay, but only if you put the orange line in between, uh, like exactly half the distance in between the red and the green points, then you will get the maximal margin. And this classifier is called the maximal margin classifier. This is also known as support vector classifier. Okay, it's clear, simple, like there is no maths involved, right? Only you are just, you know, visually uh, judging the point where you need to classify this into OBs and not OBs, right? Okay, so what if now come to the next picture? What if your data has some outlier? Okay, for example, let's say there is one mouse which is not obese but has a higher mass, right? So you have this. In this case, what will happen is that your maximal margin classifier would fail because where will be the maximum margin classifier in this case? In this case, it will be between this green point and this red point. So somewhere in between, right? But let's say then if you get a new point over here, it will be classified as not obese, but it is actually obese, right? Because it's closer to the obese set of points. So then you run into a problem. Then the support vector classifier or the maximal margin classifier would run into problems when you have outliers, right? So what you do is then you come up with a method which is called a soft margin. So what is a soft margin? So it is basically you allow misclassifications in your data. Okay, so let's say your data is outlier and you allow, let's say I allow one misclassification at least. So I by allowing one misclassification, what will happen is that you are just ignoring this misclassification. So you are allowing them and you just ignore this red point because although this is misclassified uh, as uh, as per the new orange line, this line, okay, as per the new orange line, this will be classified as obese, but this is actually not obese. So you will allow this misclassification and you ignore this point completely while building your model, and you will build your model uh, on the remaining data. So again, this will be a new margin, right? And you determine the maximal margin again based on your based by allowing one misclassification. And then this new margin is called the soft margin, and this new classifier is called the soft margin classifier, right? Is that clear up to now? Okay. Okay. So now the question is, how many misclassifications should you allow? In this case, we are allowing one misclassification. Should we allow one? Should we allow two? Should we allow three? And so on. How many misclassifications should we allow? Right? So the answer is simple. It just depends on your data and the number of misclassifications that you can allow. You have to test it on your cross validation. So this is a hyperparameter. You can think of it as a hyperparameter that you can tune, and you can just tune it on your cross validation data. For example, what will be the error if you allow one misclassification in your cross validation? What will be the error in cross validation if you allow two misclassifications? And so on. You test it and you cross validate your data, and finally, whichever number of misclassification gives you the least error, that will be the number of misclassifications that you can allow. So that is the best performance model, right? Okay, that is your best soft margin classifier. Okay. Now, let's uh, go into a little more complicated example. So let's say in case of, I mean, instead of, just a weight, you have two features based on which you have to uh, determine your support vector classifier. So in this case, you have weight, another could be, size. So you have two parameters, two features, x1 and x2. and your data, these are the green ones, let's say, which are not obese. These are the blue ones, which are obese. Okay. Now, in this case, what will be your support vector classifier? So, unlike in the one-dimensional data, your support vector classifier is just a point below which is not obese, above which is obese, right? On the other hand, in this case, your support vector classifier would be a line, okay? So, which will allow the maximum margin. And in this case, if you see the margin is this distance, this is the margin, right? Similarly, if you have a three-dimensional data, your support vector classifier would be a plane, a 2D plane, and and so on. For a four-dimensional data, it will be a 3D hyperplane, right? And so on, right? I think it's clear, right? Okay. Now, what are support vector machines? So till now, we saw what are support vector classifiers, right? Now, let's explain this with the help of another example. So let's say let's look at a different example, right? Let's say this is the dosage of medicine, okay? And uh, let's say you're taking some medicine, and the red points are the cases in which the medicine is not working. So this is a zero, let's say y equals to zero, means medicine is not working. The green points are the points where medicine is working. So if you take this much dosage of medicine, your medicine works. So if you take very low dosage of medicine, your medicine doesn't work. On the other hand, if you also take these examples, which are very high dosage of medicines, your medicine doesn't work. Whereas if you take an optimal dosage, your medicine actually works, right? So you can see, right, that this example is a little bit more complicated than the previous one. In the previous one, you had simple, you can separate this with a point. But how can you separate these examples with a point, right? You cannot have, if you draw your line over here, let's say in the second example, second picture, if you see, let's say if you draw your orange line over here, and you classify all the points to the left as not working, and on the right you are saying that the medicine is working, but that doesn't work, right, in this case, because you very high dosage of medicine also doesn't work, right? So what will you do now, right? This support vector classifier algorithm that we saw is not uh, valid in this case, right? So simple idea, what you do is you project your data set into a higher dimension. You so this is a one-dimensional data, right? You just have the dosage parameter. Now what you do, you project this one-dimensional data into a higher dimension. And how will you do that? That's the thing that we'll see in the remaining time. Okay. So Uh, you have learned about PCA and LDA, principal component analysis, linear discriminant analysis in week 3, I guess. And you see how you reduce the dimension of the data. Like somebody has asked the question about feature reduction. So you know how to reduce a higher dimension data to a lower dimension using PCA and LDA, right? If you don't know how, then you can go back to and we look at lectures of week 3, I suppose. Okay. And but in this case, what we are doing is exactly the opposite. We are increasing the dimension of data. We are taking a one-dimension data and increasing it to higher dimensions, two dimension, three dimension, or so on. Right. So what we'll do is let's take this data and map it to a 2D data. Okay. So how to do it? So let's just you look at this picture now. let's just take all the points and square it. Okay. So in this case, you take the dosage of this point. So this is, let's say, some dosage, let's say 2. The dosage in mg is 2. You square it. 2 square is 4, and you plot it in this xy plane. Okay, this is a 2D plane. So on the x-axis, this point has coordinates 2 comma 4, right? So on the x-axis, this is still this value. On the y-axis is the squared value of this dosage. So what will happen is you similarly map, all these remaining points, and this is the result that you get, right? Is the mapping clear? How it's been mapped, right? Let me, explain it with in my notepad again, if you are not clear. Okay. So let's see. Okay. So your initial data is just dosage. So let's say this has dosage 1, this has dosage 2, whereas I'm representing the. Okay. Okay, let me use a different color for. So the red ones are the ones which are working actually. So this is, let's say, this value is 5, this value is 6, this value is again 10, 12. So if you take very high doses like 10 and 12, your medicine will not work. If you take medium dosage like 5 and 6, it will work. For dosage like 1 and 2, it will not work. So you just map them into a two-dimensional space. So again, your y-axis will still be dosage, and your x-axis will be dosage, y-axis will be dosage square. So the first point, this point, will be mapped to a point 1, 1. So this is one from x-axis and one from y-axis, right? So this is the first point. This is being mapped to 1, 1. The second point will map to 2, comma 4. Third point will be mapped to 5, comma 25, right? Let me write this in red. Okay. So this point is 5, comma 25. This point is, let me, yeah, these are not according to the scale. So this will be 6, comma 36, another point. And then again, the last 2 points would be, you know, over here, 10, comma 10, comma 100 and 12, comma 144, right? So you have successfully projected them into a two-dimensional space, right? Now you see, now what you can do is you can draw a line like this, right? And thus you can separate your positive examples from the negative example, which you couldn't have done in your lower dimensional space, right? So this is the maximal margin classifier or support vector classifier, right? And your margins in this case would be the distance from this point, and the other margin would be, let's say, distance from this point. This will be your margins, right? Is the concept clear? So you're doing nothing, just projecting your one-dimensional data into a higher dimension, right? Okay. So you see, like, there is, you don't have to do any mathematics, or there are no high level mathematics involved over here.